We now take a look at an extension of the type of function that was studied quite a bit in algebra and single variable calculus. And to set the stage, let me just kind of remind you of what we've done so far with functions. And when I say so far, I don't mean just in this particular course, but in like all the previous math classes. So when we write something like this, what's actually implied is that we have a function f, that's its name, and it will take inputs from the set of real numbers or subset of real numbers, and then it will produce a real number. So you plug an x in, provided it's in the domain, you're going to get a y, right? And then we have these types of functions. Let's say these r of t, these vector valued functions. And again, when it's written like this, what's implied, again, it's you plug a single number in. So in this case, r is a function. Again, the name, the r is just the name. And then this function, it takes real values as its input, right? Again, provided t is in the domain. And then what does it output? Well, it outputs vectors in R2 or vectors in R3, right? So we know a lot about the calculus of single variable functions. We now know a bit about the calculus of vector valued functions. So what's left? Well, what if we flip this around? What if we say, okay, what if we're going to take vectors, or let's maybe even simplify it. What if we're going to take like points in the plane and plug it in, like, and do something with an ordered pair that would produce a real number? Or what if we take points in space? So we take an ordered triple, x, y, z, and do something with it and plug it. When we plug it in, the output will be a number. So it's like we're literally going to flip the script. I've always wanted to say that, right? We're going to flip the script on this and say, let's use these sets as domains, right? Or subsets of R2, subsets of R3 as domains. And then let's output just real numbers. And this is what we mean by functions of several variables. At least these are two examples. So what the phrase several variables, what that's meaning is that the input is not just a single x or a single t, but it could be an ordered pair. It could be an ordered triple. It could very well be an ordered quadruple. Wow. Like in four-dimensional space. And then what we're doing now is whatever rule, whatever the equation is that we actually end up with, the output will be just a number. All right. So that's the idea. So what do they look like? Well, it turns out they're going to look a lot like this, like these, I should say. But instead of having just an x as an element from the domain, again, we're going to look at either xy, xyz, or maybe xyzw. So you'll get, so for instance, this one right here, these are just the standard letters. So we're going to say that z is going to be a function of x comma y. So that's what they look like, right? So the several variables, again, is going to be referring to the number of independent variables. These functions will still have just one dependent variable. So this equation is implying that z is a dependent variable of x and y. But what would something like this look like? Well, the typical letters that are used in this case, we usually use w as the dependent variable. And then again, you can still use F or G or H. That's the standard lettering. But now, instead of having an ordered pair in parentheses, we have an ordered triple. So it looks like that. And I know this is not, so like if you were to think of this your total, if you include the dimension of the domain and the dimension of the codomain, you end up with 3. In other words, you have 2 numbers in and 1 number out. So like for instance, over here, when you have 1 number in and 1 number out, it usually gives rise to ordered pairs. And then we could plot them and get curves. Over here, when you have 2 numbers in and 1 number out, this tends to give rise to an ordered triple, right? And then, so over here, this is where you'd get 3 numbers in, 1 number out, so you would get a point, so X, Y, Z, W. And don't worry about it. I know it's not alphabetically correct, but that's the standard variables used in this instance. There really aren't any standard variables used in this, but let's say we had like Q be a function of X, Y, Z, W. So what this would mean is for this ordered quadruple, then this would be the associated output. So think about what that would mean. You'd have to plot whatever this would look like. You'd have to plot it in a 5-dimensional space. So it would be X, Y, Z, W, Q. And very soon, so in general, so if we continue this pattern, you technically can have a function of n independent variables, right? And then the output would still be a single real number. So you could say something like this. I'd say y. You may say, well, how am I going back to y? Well, this is what I'm going to use now, since I have essentially, it's a finite number, but still arbitrary, meaning in the sense that it's some positive integer. I just don't know what the integer is. Well, what I can do, I can just use subscripts and say x1, x2, x3, ... xn, right? And then so think about this. You'd have an ordered n tuple plus 1, because you'd have all of these being elements in, or defining an element in the domain, right? The stuff you're plugging in, and then you'd still have a single thing out. So essentially, we would have to account for these n variables plus this other variable. Pretty, wild stuff. But again, so for instance, let's say you've taken a course in matrix / linear algebra. Yeah, you're okay. You're okay. You're comfortable with the concept of having lots of variables going way beyond just 2 or 3, right? Now, our focus will be on these, right? This will be our focus. And just to give you an example, not just of the ones that we're going to focus on, but ones that, it's not out of the realm of possibility. In fact, it's more common for you to have functions of this form than functions of this form. Because, for instance, in a real world sense, what this equation is saying is that you have a single, you have some variable that is affected by only one thing. But in the real world, usually things like one thing might depend on several different things. So you actually find that these functions are a lot more useful than these, right? So why don't we start with this, back in good old algebra, where they say, well, let's talk about functions. Well, we have to start somewhere, right? These are certainly easier to graph. They're easier to kind of introduce the concept of domain, codomain, range, and on all the operations that go along with functions. So let's just look at a couple examples. This won't be in fact, this video has gone on longer than I expected, but just wanted you to get a sense of the notation and what exactly we're talking about. But let me show you that some of these things are a lot more practical than you think. So let's take an example like this famous equation. your PERT model. Now, if you remember this, this is for, let me write it in a different color. This comes from continuous compounding. All right, so this is like one of those, financial type questions. So this is continuous compounding. You have a principal amount. So this is like your initial deposit, if you will. You have it's typically an annual interest rate. And then, your T would be your number of years of investment. So let's just say term of investment. Usually it's in years. And then A is how much you have left at the end of that term. And now this assumes no additional deposits or withdrawals. So it's a very simple model. But again, it's the basis for a lot of important financial mathematics. So A is the amount present at the end of term. Why are we doing this? Well, if you think about this, the only thing on the right-hand side here that is a true constant is our wonderful number E. In other words, your principal can vary, right? Your interest rate will definitely vary, right? And certainly your term length. Are you just going to invest it for a year or 5 years or, 20 years? You're a long hauler, whatever it is. Although the phrase long hauler implies something different nowadays. But so really what is implied here, if I don't assume that P, R, and T are constants, I have that now A is a function of my principal, my interest rate, and my time. There you go. So, or in fact, let me write it like this more clearly. So you have your A, and then it's equal to that, right? So right away, in such a simple model, right? If you really let these things play a realistic role, then yeah, these P, R, and T could change independent of each other. That's why they're called independent variables, right? But regardless of how much or how little they change, they do have an effect, right? They do affect the amount, right? So that's one thing. So that's kind of a financial one. Another is look at something like this. Volume times width times height. Famous formula, right? For the volume of a rectangular box. This is something that we can actually draw. We can actually visualize this thing, right? So here's my box. And it is somewhat of a rectangle. Pretty good, right? And yeah, so, you have your length, you have your width, you have your height. And again, when you're thinking about these, when you look at boxes, even when you go to a packing store and you see the boxes, and sometimes they have the boxes on display to show you what it actually looks like. You see, some are taller, some are flatter, some are wider. Yeah, so these dimensions are all variables. So again, what's implied when I write something like this is that my volume is a function of length, width, and height, right? I'll do a third one, and this is this one I will start with the concept of space-time. You hear this a lot, the space-time continuum and all this stuff. And, then you talk about Einstein's theory of relativity. I think probably his special one. Yes, actually in both. But this idea of space and time. And in essence, like one fundamental concept from his theory of relativity is that an object, like the state that an object is in, and when we talk about that it's like, think about its motion, Think about like the life of a star. Is it just being born? Is it about to die? Things like that. Or black holes. Are they just gobbling up things around them, or they're relatively stable? Things like that. So when we talk about like the state of an object, Einstein says, well, yeah, it is a function of the position in space and also time relative to some other event. Maybe it's the Big Bang or something like that. And then you get into Stephen Hawking's um, theory of the evolution of the universe, things like that. So okay, what does this have to do with functions of several variables? But think about how we define space. In our rectangular coordinate system, we define space in terms of these three variables, x, y, z. And then you think about time. So like when those vector valued functions, when we talked about motions or motion, right, we use the variable t. So in a sense, when you talk about space time, you're talking about a function that depends on where you are in space and what is your time or age relative to some reference point, right? So there you go, a function of four variables. And again, you don't have to get this abstract, to find examples like this, but I just wanted to pick a whole bunch of different examples so you can see that, again, I will argue this to the death. Hopefully it doesn't come to that, but I will argue that these functions where you have something, a quantity being dependent on several variables, right, is a lot more realistic and a lot more practical than your y equals f of x, right? But you had to start somewhere. So what are we going to do with these wonderful functions? Well, think about it. We're going to learn about, the basic algebra of those functions, as well as the important things in calculus. So what are some of the important things in calculus? Limits, continuity, differentiability, integrability. And yeah, so we're going to learn what it means to differentiate these, integrate these, and then again, optimization, area, volume, all these different quantities. And we're going to see basically an extension of what our previous work in calculus was all about. Now, as far as the algebra goes, let me just do a couple quick examples to wrap this up. So let's go back to let's start with the function that just deals with ordered pairs as the input, and you get an output. So let's say, so let me give you some like usable notation now. You might say something like z, is that's our dependent variable, is a function of, let's say it's just something like x squared plus y minus y squared, something like that. That would be a function that we're going to learn to do a lot with. Another notation could be, you could use the letter f, right? And then you actually, in parentheses, indicate the independent variables, in this case x and y, and then you can still have the rule. And when I say rule, I mean the statement that tells you, or the expression that tells you what the function does. Like, what does the function do to these input values? So it's very similar notation. And then as far as, let's say we wanted to evaluate this function. So if I wanted to take this function, and if I wanted to do, let's say 2 comma 4, let's see what happens if I plug in x equals 2 and y equals 4. Now, when you do something like this, we have to have a certain order in mind. Otherwise, it will be ambiguous. And we're going to use the same order that we use when we're denoting standard ordered pairs. The x value is always first. The y value is always second. If we had a third value, that would be interpreted as a z in this context. If the context is a little bit different, then the question would have to indicate like the order, right? So in this case, it's the square root of 2 squared plus 4 minus 16, right? Well, that's a problem, right? So we got a problem there because this is 4 plus 4, that's 8 minus 16. And then this is the square root of negative 8. And again, if notice, if I say I am looking for a real output, in other words, an output that is a real number, this does not exist. So the same way, if I just gave you a function of a single variable and you evaluated it and it was a square root and you ended with a negative number under it, unless it's a course that you're now using complex numbers, which this is not that course, right? Then we would still say that this is undefined. So what that means is the ordered pair 2, 4 is not in the domain of this function, right? So, and in a subsequent video, we're going to do a few more examples of domain, but I just wanted to show you, as far as the algebra of these functions is concerned, it really is just a natural extension of what we've done before. All right, so we're gonna end this video now and see you in the next video where we continue talking about these, fanciful functions of several variables. See you then.